This video marks the start of a series I'm going to be doing on Newtonian physics, where we're going to look at things such as motion and forces, work and energy, and things like that in future videos. But in this video, I'm going to start by looking at the simplest case, which is motion in one dimension. So let's imagine a scenario here where we have a car, and I'm drawing out a nice looking car here. And we're going from one position, starting at one position, which we'll call x1, and we're moving this way to end at x2. So we have a start position and an end position, which have a distance between them. So this distance, I'll draw it like this, is delta x. Now this distance, I say the word distance, is actually displacement. And so let's define displacement. Displacement is the difference, I should say, let me rephrase that, the shortest distance between 2 points. And it's a vector. So it is a distance in some direction. We have to specify the direction. So the distance, now what's the difference between distance and displacement? That's an important distinction to make. Distance is the scalar version of displacement, or you could say distance is the magnitude of displacement, at least in one dimension. In more than one dimension, they're different. But in one dimension, the distance is just the magnitude of the displacement. Okay, and so we can characterize our displacement as this point minus the starting point. And that is our displacement. Now another thing we have here is a time difference. So we can't be at two places at once. We have to start at some time t1 and arrive at the finish point at a later time t2. And so our time also has an equation associated with it, which is that our change in time is equal to t2 minus t1. Now, using these two variables, these two equations, we can come up with a third. And what we can do is ask ourselves the question, how does distance slash displacement, how does this change with time? So if we travel to this point, how long does that take? What about this point? We can figure out how fast it takes us to get to a certain point. And why don't we ask ourselves how far it takes to get from x1 to x2? Well, that looks like this, and it is given by a quantity called velocity, which is our position divided by our time, change in time. Where, this isn't a vector quantity right now, but, we're moving. We'll call this the positive x direction based off, our regular convention that this is positive x-axis, this is positive y-axis, and we're only in one dimension, so we only care about x. So we're moving the positive x direction, so I will give this an i-hat direction. But let's forget about the vector for now. Let's just consider these variables. So v is equal to delta x over delta t, which is x2 minus x1 over t2 minus t1. and this is velocity. Now, one thing to note here is we're only considering the end point and the starting point here. We're not considering any point in between. So as far as we know, these points in between don't matter. And therefore, it's an average velocity. We could be traveling at different velocities at any point along here. Like we could accelerate, decelerate, go at any velocity, but we don't know that. We don't know what's going on between the points. We are just taking the end point minus the start point, and therefore we're getting an average velocity across the whole range. So let's now dig into what this really is saying. Let's understand intuitively what this means. If we look at the velocity, we have our delta x, our position, our displacement, in the numerator. And this means that the velocity and the displacement are directly proportional to each other. Directly proportional. It's not very neat writing, but directly proportional. And so this means if you increase the velocity and keep the time the same, then your velocity will increase as well. So if we go from x1 to x2, and we do this in 1 second, then we double this. So I'll draw this in red, and we'll call this delta x. And then in red, this is 2 delta x. And we travel that also in 1 second, so the time is the same, but we're doubling the distance. Then our first equation in the black is v equals delta x over delta t. But when we double the velocity and keep the time the same, v is equal to 2 delta x over delta t. So velocity doubles. Now, time, the velocity is proportional to the inverse of time, so they are inversely proportional to each other. So drawing out similar thing, we're traveling from x1 to x2. This is delta x. And we go, first time, we do it in 1 second. The second time, we double it. You know what? I'm going to just call this delta t. And we double it, so we're taking twice as long. Now it's 2 delta t on the second time. So the first scenario is just the same. We're taking delta x in a certain time, delta t. But when we double the time, we're doing it delta x in twice the time. And so velocity is halved. We cut it in half. And therefore, it's inversely proportional. And so that is sort of an intuitive introduction to some of these velocities and displacements and times and how we can calculate in one dimension. In the following video, I will do an example. Actually, I will do 3 examples on how we can use this information to calculate velocities and various variables that are relevant. So I'll see you in that one, and thanks for watching.